The concept of teleportation has long fascinated both scientists and the general public. From science fiction novels and films to speculative scientific discussions, teleportation represents the ultimate solution to one of humanity's oldest challenges, the limitations of space and time. In essence, teleportation involves the instantaneous transfer of matter or energy from one location to another without traversing the physical distance in between. While currently limited to quantum experiments involving particles, the theoretical underpinnings of teleportation raise profound scientific, technological, ethical, and societal questions. Could teleportation, if mastered, replace planes by the year 2300? This exploration aims to evaluate the feasibility of such a development, rooted in modern physics, speculative technological advancements, and the broader implications for humanity. Teleportation first entered the popular imagination through science fiction. From the transporter in Star Trek to numerous depictions in novels and cinema, teleportation was portrayed as a convenient, safe, and instantaneous means of travel. These fictional accounts often oversimplify or bypass the immense scientific complexities associated with such a process. The scientific community began to approach teleportation in a more rigorous manner in the 20th century, particularly with the rise of quantum mechanics. The discovery of quantum entanglement, first described by Einstein, Podolsky, and Rosen in 1935, laid the foundation for real-world explorations of teleportation at the quantum scale. The first experimental demonstration of quantum teleportation occurred in 1997, when researchers successfully transmitted the quantum state of a photon over a short distance. This achievement did not involve the transfer of the photon itself, but rather the transfer of its quantum information. Since then, progress has been made in teleporting quantum states across increasing distances, even reaching hundreds of kilometers via satellite-based experiments. At its core, teleportation relies on quantum entanglement, a phenomenon in which two particles become linked such that the state of one instantaneously influences the state of the other, regardless of distance. This counterintuitive feature of quantum mechanics enables the possibility of transmitting information in a way that bypasses classical communication channels. The process of quantum teleportation, as defined by Bennett and colleagues in 1993, involves several crucial stages. First, a pair of entangled particles must be created and distributed between the sender, often referred to as Alice, and the receiver, Bob. The sender then performs a joint measurement on her particle and the system whose state is to be teleported, collapsing the wave function into a definite outcome. Finally, the results of this measurement are sent to the receiver through ordinary communication methods, allowing Bob to apply the correct quantum operation to his entangled particle and thereby reconstruct the original quantum state. Importantly, this process does not transfer matter itself, but instead transmits quantum information. The reconstruction of matter would demand an even greater level of technological sophistication. The difficulty becomes apparent when considering the scale of teleportation. Moving from single photons to molecules, and eventually to living organisms, requires capturing and transmitting information about astronomical numbers of atoms. A human body, for example, contains roughly YY atoms. Encoding and reconstructing this information remains far beyond current scientific and computational capabilities. Although human teleportation remains firmly in the realm of theory, several possible approaches have been discussed in scientific and speculative circles. One approach envisions a complete quantum reconstruction of the body, in which every particle's state would be measured, transmitted, and then rebuilt elsewhere. However, the no-cloning theorem in quantum mechanics prevents the creation of identical copies of unknown quantum states, which means the original body would be destroyed during the process. This introduces unsettling ethical questions regarding identity and continuity of consciousness. Another line of speculation involves bypassing quantum states altogether in favor of ultra-precise molecular scanning. By mapping every atom and its bonds, one might transmit the necessary data to reconstruct the body at a new location using raw matter. This idea is conceptually simpler than quantum reconstruction, but the data involved would be unimaginably vast, likely exceeding the total communication capacity of our entire planet. A more radical possibility involves manipulating space-time itself. Theoretical constructs such as wormholes, suggested by general relativity and string theory, could in principle allow matter to move instantaneously across great distances. Such ideas remain entirely speculative, however, and face enormous hurdles related to stability, energy requirements, and the potential for violations of causality. The question of whether teleportation could replace planes by 2300 depends on both technological progress and societal acceptance. The obstacles are formidable. The computational power required to store and transmit the data of even a small organism is far beyond what today's most advanced supercomputers can handle. Likewise, the energy needed to disassemble and reassemble matter at the atomic scale would be astronomical. Even if these hurdles could be overcome, the process would demand extraordinary precision, as small errors in reconstruction could prove catastrophic for living beings. Beyond technical challenges, there are profound ethical and philosophical considerations. The destruction of the original body in the teleportation process raises questions about whether the traveler remains the same person, or is simply a perfect copy with identical memories. Privacy concerns would emerge as well, since the ability to scan and store an individual's complete biological blueprint could be exploited or misused. Furthermore, access to teleportation technology could exacerbate inequality, offering tremendous advantages only to wealthy individuals or nations. From an economic and societal perspective, the advent of teleportation would disrupt existing industries and geopolitical structures. The airline industry, tourism, and even the significance of national borders could be profoundly altered. Physical distance would lose much of its meaning, reshaping global trade and politics. Looking ahead, one might envision a series of milestones necessary for teleportation to become viable. In the coming centuries, advances in quantum teleportation, quantum computing, and theoretical physics will likely continue. By the 23rd century, it is conceivable that experimental systems capable of teleporting inanimate objects might emerge. Progress in biological sciences might even make the teleportation of simple tissues theoretically possible. However, the leap to safe and reliable human teleportation would demand further breakthroughs in data processing, error correction, and ethical acceptance. Even with optimistic projections, it appears unlikely that teleportation will fully replace planes by 2300. Instead, more limited applications, such as the teleportation of cargo or specialized materials, may coexist with conventional transportation. Teleportation forces humanity to confront some of its deepest philosophical and ethical dilemmas. The continuity of identity is one such issue. If the original body is destroyed and only a perfect copy survives, can we truly say the same individual has traveled? This question cuts to the heart of what it means to be a person. Issues of consent also arise. Would travelers agree to such a procedure knowing the risks of data corruption or potential loss of selfhood? Clear legal and ethical frameworks would need to be established. The broader societal consequences are equally complex. The potential misuse of teleportation for espionage, terrorism, or even unauthorized replication of individuals presents risks that cannot be ignored. Just as nuclear technology reshaped the 20th century, teleportation could become a defining challenge of the 23rd century, requiring new forms of regulation and oversight. Teleportation remains one of the most tantalizing yet elusive possibilities in both science and science fiction. Current achievements in quantum teleportation represent only the faintest glimpse of what might be possible in the distant future. While the notion of teleportation replacing planes by 2300 is unlikely given current scientific understanding, the exploration of its feasibility illuminates fundamental questions about physics, technology, ethics, and human identity. The dream of stepping into a machine and emerging instantly across the globe may remain unattainable, but the pursuit of such knowledge continues to expand the boundaries of human understanding. Whether or not teleportation becomes a reality, the scientific journey toward exploring it will inevitably shape the technological and philosophical landscape of future centuries. This was a speculative exploration by the Tech Prophecy. If you want more thought experiments at the edge of science and imagination, subscribe and stay awake with us.